Alright, today I will be explaining probability and integration and how to apply that in real world scenarios. So for a review problem, I came up with finding the area from below the graph of y equals f of x for 3 is less than or equal to x, which is less than or equal to 5. So basically from this information, we know that this is going to be the lower bound, and this is going to be the upper bound of our integral, which will be defined by f of x as stated in the problem. So I'm going to take this off my stand so I can write properly. So we're going to create an integral with the given information, and in order to do this, we just need to apply what we know. So we know that the integral is going to be from an upper bound of 5 to a lower bound of 3, or 3 to 5. And then we're going to write f of x and then the antiderivative of that as we do the integral. So this is going to be equal to this, and then we're going to apply the formula or the equation that was given. And whenever we find area, we always are typically finding it between two of the bounds in order to give us a definite answer. So now we are going to solve this integral. So we're basically just finding the antiderivative, and we're just going to keep like this, and then add 1, and then we know that this just adds 1. And then we cannot forget our bar, which shows what we're going to eventually plug in. And if you'd like I am, I'm going to be simplifying this down as much as I can in order to give us an easier problem to set up. So it'll go like this. And I'm going to put this in a big parentheses so we know what we're multiplying and adding together so we don't get mixed up. So we're basically just plugging the lower or the upper bound in, and then we're going to do the same with the lower bound, and we're going to subtract that from each other in order to give us an area. So this is a 3, really bad looking 3. And then like this. Oops. Why'd I put a 5? Oops. This is new. And then once you plug that in, you're going to get pretty large number. Not really expecting this when I wrote this problem, but that's all right. It's going to be this. This is going to be the area after we plug that into our calculator and solve. All right, so now that we have an idea of kind of what we're going to be doing and applying this, we're going to move forward. So in probability theory, we have a variable x, which represents the event that we are analyzing, which is then called a random variable. And with this, we know that probability that the value of x lies in a given range, a to b, kind of like the problem we did before. And note that this is going to be capital and whatnot. Okay, so that's notation. And for random variables, we know that there are two types. We know that there are discrete and continuous. So discrete, you can only take finite numbers of values, which I'll kind of further explain. And then on the continuous, you can only take on, or you can take on any value in a given interval. So let's see, I think I have some examples which we are going to be labeling. So from this info, are they going to be discrete or continuous? It's kind of a review of things probably discussed in Calculus 1. So amount of wins in Minnesota Vikings 2023 to 2024 season. This is going to be a discrete value because it's going to give us a number, that we can count to. If that makes sense. It's not continuous. And then the wind speed in Olmsted County, this is actually going to be continuous because it varies. And then the number of students taking Math 2171 is going to be discrete as well. You can count it on your fingers. Very nice. All right. Hopefully you got those. If you didn't, I'd go review. All right. So now we get into what we're actually going to be discussing, the probability density function, or PDF, otherwise known as. So this is where P of X is going to be where the probability is defined by this range like we were given before, the lower bound and the upper bound. And then we're going to apply that to an integral. And keep in mind that X is going to be this random variable and P of X is a continuous function. And it's for only continuous random variables, which is pretty important. So please keep that in mind going forward. So some assumptions we're going to have to make in order to apply this is going to be that the probability density function P has a domain J. That is an interval where J contains all possible values of X. All right. And then we know that the possibility that J is an event that will happen as infinite interval, kind of elaborating on how it's continuous. And then the P of X is going to be greater than or equal to 0 for all X in the domain because the probability cannot be negative, which makes sense because you can't have a negative 12% chance that it's going to rain, if that makes sense. All right, and this is just it written out notation-wise, so keep that in mind. So when it's not bounded up here where it typically would be, it's going to equal 1. So event happening at this is always just going to be 1. Okay, and then I kind of have an explanation slide for those who are curious. Not really going to be touching too much on this as it's pretty easy and concrete for explanation-wise. So I'm just going to briefly read over this. So we assume that a probability density function, P, has a domain of J, kind of what I said already, and that J contains all the possible values of the random variable X. We allow that possibility that J is an infinite interval. Furthermore, P must satisfy 2 important conditions and must be greater than or equal to 0 for all X because it cannot be negative. And then it's just elaborating again on this really important formula, and it's pretty easy to memorize that. And then something that I want you to notice is that the integral in this equation is evaluated over the whole domain that represents the probability that the value of X is in its domain. And this integral must equal 1 because it is certain that the value of X lies in that J by the assumption that we already made up here, that it's an interval and it contains all possible values, so just keep that in mind. And then that the integral of P over J is 1, that ensures that, that the probability is bounded by A to B for all X in its domain, as said here. And it's a number in the interval 0 to 1 for any A and B in the domain. Okay. So now that we know that, we can apply that to this example that I have written out here. So this is kind of just going off of things that we were talking about earlier. So we're just basically plugging this into an integral and then plugging in the bounds 1 to 3. And keep in mind that we're going to be using a trig identity here. So keep in mind that this is going to be related back to tangent. That's a hint, I guess. All right. So let's apply this on the next page. So a quick reminder that you should probably keep in mind is that the integral that is defined by this, and keep in mind this can be written over here too, but no need for that. It's the limit of n, or I should say r, negative infinity, tan 0 to r. And furthermore, that can just be written as this. And this is going to be important for when solving this integral, so just keep in mind that it's going to be the inverse of tangent. And then in any other problem that we would do, we would plug this in, hoping that would give us a real answer. So we know that this is going to give us 0, and we're going to subtract. It's important. And then tan of r is going to be pi over 2. And apply some algebra. That's going to become a plus, so it's going to be a positive pi over 2. All right, so now that we know that reminder, we're just going to keep that aside going forward. I'm just going to keep it right up here. All right, so for this problem, similar to, the last one, we're just going to go like, go like that, if I can get it to work. Okay, and then a p of x of dx, okay, and then we're going to apply a constant out front for negative infinity to 0 of dx, similar to what the reminder said, and make sure that you know that you have to apply both sides, so we have to do 0 to infinity as well, because to match. All right, and then like previously said, we're going to go like that. And then we are going to apply the integral. So we know that this antiderivative of this when applying tangent is just going to be 2. And then same thing for this. I should go like this. It's also going to be the c pi over 2, and we know that the c is constant, so we can add alike terms, and that's just going to be pi. And we know that this is going to be equal to 1, okay? So now that we have that, we are going to apply bounds, which I'm going to write in red over here, for p x. Go like that. Okay. So we're basically just plugging in values that we know and that are given. And then once we plug that in, it's just going to be this pi inverse of tangent inverse of 3 minus tangent inverse of 1. And this value, I have to plug this into a calculator, but it should be 0 point something. So I don't have a calculator on me right now, and it's not solved on my answer key note sheet. So we are going to say that this is going to be, we'll just say 14, okay? Say it was 14. So we would turn that into a percentage, multiply that by 100. So 14% probability that x lies between 1 and 3. Okay, so that was the first example, and the next example I have is kind of just elaborating further on this, but I don't have an example for this. So we're just going to look at what the book says. So for this, we're going to be looking at the mean of a random variable with exponential density. So as we all know, the mean is defined as the sum of the terms divided by the number of terms. So that's like A plus B plus C. There's 3 terms. That's going to give us our bar over x, which is then translated to the average. All right? So for this example, we're just going to take a look at it and then see what we can find out based on the information given. So we're going to let r be greater than 0, calculate the mean of the random variable with the exponential probability density of p of t equals 1 over r e to the negative 2 over r on the 0 to infinity bound. So for this, we'll be using integration by parts to solve for the mean of the random variable because it's exponential, and then note that this has to be continuous in order for it to be like applied. Okay, so for this is the book's explanation, but I'll just be walking through it. So the mean is the integral of t over 0 to pi, which is why, do I have a laser? Yes, I do. So multiplying that by the pt because we're finding the mean, right? So using the integration by parts, we're going to put u equals t of r, which will be applied right there once we plug that in, and dv equals e to the negative t over r dt, where du is dt over r, so they derive that from that, and then v is going to be the direct translation to that. So the antiderivative of dv, which is negative r to the e, or negative r times e to the negative t over r, okay? So then they set it up, so they're going to multiply this out front because it's the mean, we're doing the mean, and then they plugged in p of t, which was given in the problem, all right, back here. So technically this would be a 1, but since we're multiplying it by t, they just put it up front right there. All right, so dt, and then what they did, we're solving the integral by parts, so we're just taking it out and then putting it back in, and then further applying that and simplifying it. So from that, we get this lovely looking thing, and then we simplify it even more over here. And I should say back here that technically for this, instead of using this notation, we're just going to be using mu. Okay. So for mu, the mean is given by this integral, which we already kind of looked up here and solved for. And they're just going to be plugging in the bounds of 0 to infinity. And then they're going to be plugging in the r and the 0 again. All right. And then that's going to be equal to little r. Okay. So the last equality holds r plus capital R times e to the negative capital R to over r as it approaches 0 and as capital R approaches infinity. So it must follow that it follows that the mean of the random variable with the probability density function of pt over 0 to infinity is just going to be little r, okay? can't really reply back, but that's how it's kind of integrated into using the exponential values and applying that like up here, for example. Okay. So, I have this example, but I do not have, I don't like the way it's written, so we're going to skip over it. Okay. So, there's that. And then another side note that I made is that PDF, or probability density function, is commonly used to model waiting time between events. So this problem is also given in the textbook, but I also made my own, which is applicable more so in the medical world. So we're going to try this one out first. So we're going to practice notation. So we were given that the average waiting time is 60 seconds. So let's just write down some quick values that might be a little bit helpful later on. So the average waiting, 60 seconds. And we are going to assume that little r is equal to 60, okay? And this is a pretty standard formula, but for that, it's going to be like this. E to the negative r, I meant t over r. And then once we apply this, that's just going to be equal to 1 over 60 times e to negative t over 60. All right. So we know that is what we're going to be plugging in our values to once we solve for the antiderivative. And we also, we know that the interval that we're solving for to see like the percentage of times that it's going to land between 30 seconds and 45 seconds, that's going to be defined as this, which is going to be applied to the upper, lower bounds. Okay. So once we have this information, we can plug it into our nice little integral. So 45 and 30 seconds are the times we're going to be solving for, and then we're just plugging in this nice formula that we were given right away. That's going to describe the P of t for waiting time. So I'll go like this, and then that's going to equal negative e to negative t over 60 once you take the antiderivative of that. If you don't know how to do that, there should be a formula sheet with like the derivatives and the antiderivatives that you can take from that. So we know that this is just going to be this taken out front, and that's going to cancel out basically, and you're left with this. So then once we do that, we are going to apply the bounds that we were given, and then we're going to solve by plugging it in. So it's going to be 45 divided by 60, make sure that's negative, and then it's going to be negative, and then it's going to be positive because we're subtracting a negative value, and same type of thing. Okay. And we know that this can actually be simplified more just to make it easier on comprehension levels. Like, it just makes more sense to see this simplified out. All right. And once you plug that into a calculator, you should be getting 0.134. And we know that we can apply the times 100%. Should have learned that in like 6th grade or something, right? So 13.4% is what we're given. So then we can conclude at the end. Sorry, I want more color, so it's a little bit more exciting to look at once we're done here. So 13.4% chance that the waiting time, or I should say waiting period, for the next customer will be 30 to 45 seconds. And then I guess you could put in parentheses for average waiting period of 60 seconds. Okay, so that's kind of how we're going to write that for now on. So we're going to do a similar problem, but it's going to be a little bit more UMR-esque what we're looking at. So this application problem says that heparin used by injection is given to reduce blood clotting. Typically works within 40 minutes after initial injection. Given that waiting time for the medicine, give the probability that the heparin will be effective from 20 to 35 minutes, so half to like 3, or a little bit over 3/4, I should say, of that waiting time. And we're given some hits. Come up with an integral applicable to the waiting time. We know how to do that. And then apply probability from time A to time B with the bounds. So we know that this, similar to before, we're going to know that this is actually going to be our little r, and this is going to be bound. It's going to go lower bound. Or is this going to be upper bound? All right. So take a look at that. It's okay because I got my little answer key. That's really nice, handy dandy over here. So let's do something that's a little bit more exciting to look at. Okay. 1 over r equals negative t, and this is pretty standard for waiting time. And note that r is going to be equal to 40 minutes, okay? It doesn't really matter unit-wise. It's all going to work out the same as long as it's consistent throughout the formula, okay? So we know that the probability, 20, okay? Then we're going to apply that to an integral, 35, 20, and then we're going to plug in that formula that we've been using. And what's nice about this is that it's just going to be the same every time. So if you know your antiderivative of this guy, it's just going to stay the same with little r being different each time. So we have that upper bound and then the lower bound. And then we're just going to plug it in like before, and it's going to give us a nice-ish number. Hopefully negative makes a positive. That's negative 20. Oops. And you could simplify that, I guess, down to 7 over 8. Yep. Or 1/2 if you wanted to, but it's all going to turn out the same. So once I plug that into my calculator, I'm going to get 0.0713. And then at this point, we should know that this is going to give us a 7.13% chance. Okay? 7.13% chance that the heparin will be effective. 20 to 35 minutes after initial injection. And that is how you do those problems. So basically, to recap what we did, if you get dizzy, don't look at this. We're just going to go back. So we learned about the probability density function and how we're typically given a lower and upper bound, and we're told to solve for the percent or the probability that such event will happen. And you always have to keep in mind that this is going to be, so for the last problem we did, it was a capital T for the time, but it's always going to be a random variable. And keep in mind that the p of x is always going to be a continuous function in order for us to solve or to apply the PDF. And keep in mind the assumptions. If we're just given a one lower bound, it's always going to equal that one because it's just one event, if that makes sense. One event that we're counting on. Therefore, the percent that it's going to happen is just going to be 1 or 100%, I guess you could say. And then we went through our example and learned how to apply bounds and kind of traced our memory with trig identities.